the sound shows up in the recordings, but yeah, so today we're going to talk about sequences and maybe introduce series, because sequences is not the longest section. And a sequence is not anything very special sounding when you put the definition on the board. A sequence is just a list of numbers. And the key here is that at least in a calculus 2 context, we're thinking of sequences as being infinite lists of numbers. So, I mean, I said not very interesting. I guess it depends on your point of view. I mean, the ancient Greeks did not have a concept of infinity. So to them, this would be quite curious. To us, it's probably not a huge deal. I mean, you can imagine listing out the primes, for example. And you probably know that there are an infinite number of primes, so this is an infinite list. Or you could imagine listing out the perfect squares or whatever. And sequences are infinite lists. Notice that they do have starting points, so they don't have ending values, but they don't go in both directions. They do start somewhere. And we can describe sequences in a few ways. And for the purposes of this class, we're going to almost exclusively describe sequences in one way, but let's just go through the options. So when we write a sequence down, I guess we can start with notation first. If you're being sort of full formal, writing a textbook, being as, notationally correct as you can, a sequence is written something like this. And this is actually very similar to summation notation, where we have a starting value and an ending value, but sequences are infinite, so the ending value is written as infinity. So this is x sub 1, x sub 2, x sub 3, x sub 4. And, if we had a finite sequence, that would be the stopping value. Here's the sequence from 1 to 5, but we'll be looking at infinite sequences, so we don't stop. We just keep going on forever. And that n equals 1 probably makes sense. The first element of the sequence we'll call x sub 1. You do sometimes see situations where we want a zeroth term, and then we start from 0 to infinity. And that's mainly a programming thing. Like, depending on your language, you've got while loops and you've got for loops, and you're starting at either 1 or infinity, depending on the language. So how do we define a sequence? Well, in one sense, I guess the easiest way is just to do it verbally. X sub k is the kth prime. There's a description of a sequence. So x sub 1 is the first prime number. The first prime number is 2. 1 is not prime. X sub 2 is the second prime number. The second prime number is 3. X sub 3 is the third prime number. That's 5, and so on. So, convenient in a sense. Inconvenient if you want to know what x sub 100 is, because to find that out, you'd have to go to a list of prime numbers and find what the 100th prime is. So perhaps more convenient is having a formula that describes the elements of the sequence. And this is the method that we're going to be studying in most of calculus. You could say, for example, well, x sub n is n squared divided by n squared plus 1. And this is basically a function. In fact, in one point of view, from a set theoretical point of view, it is a function. You can think of that subscript there as being an argument. And, if we have x sub 5, we go over here, and we stick 5 in. Everywhere n shows up. So that's another way of defining a sequence. The downside of this is that in a lot of real world situations, no one's going to give you a sequence like this. I mean, no one's going to give you an equation. The other main way of talking about sequences is recursively. And a recursive definition is one where, let's say, x sub n depends on x sub 1, x sub 2, up to x sub n minus 1. So every element in a sequence, in a recursive sequence, depends on the elements before it. And we might not need all of the elements before it. A lot of times it will just depend on the immediate predecessor. For example, x sub 1 equals 5. X sub n equals x sub n minus 1 squared plus 2. And you'll notice that to define a sequence recursively, I've given you two pieces of information. I've given you this equality. What we have here looks a lot like what we had there. And I've given you this so-called initial condition. And we need both of those to define a sequence recursively. So x sub 2, for example. So here n equals 2. X sub 2 equals x sub 2 minus 1 squared plus 2. That's x sub 1 squared plus 2. X sub 1 is 5. Here's where we need that initial condition. 5 squared plus 2, 27. So you see, to find x sub 2, we needed x sub 1. And to find x sub 3, we need x sub 2. Where again, in the situation where if we want to know what x sub 100 is, it's kind of a difficult situation, because to find x sub 100, we need to know what x sub 99 is, but to find x sub 99, we need to know what x sub 98 is, but to find x sub 98, and so on. So to find the 100th term, we need to find every other term between 1 and 100. We're not going to use this a lot in this course. It shows up all the time in computer algorithms. I mean, most computer algorithms are the user provides some kind of guess, and then the algorithm uses that guess to compute later terms. Sorry, So I was saying that yes, that this shows up a lot in like algorithms. Like there's no real reason anyone would remember this. We spent a day on it a semester ago, but we looked at a root finding algorithm in Calculus 1, Newton's method, which is something like x sub 1 equals some kind of user inputted guess, and then x sub n plus 1 is x sub n minus f of x sub n over f prime of x sub n. And this is a root finding algorithm. The idea is that if you've got a function and you've got the x-axis and you've got some root that you want to find, the user will input a value kind of near the root. There will be x sub 1, and there will be x sub 2, and x sub 3, and x sub 4, and x sub 5, and these are getting closer and closer to the root. So lots of stuff like that. There's a very famous sequence. I used the word famous a little advisedly, but called the Fibonacci sequence. Where we rely not on just the last value, but the previous two values. So we define x sub 1 to be 1 and x sub 2 to be 1. And then x sub 3 to be x sub 1 plus x sub 2, x sub 4 to be x sub 3 plus x sub 2, and in general, x sub n to be x sub n minus 1 plus x sub n minus 2. The Fibonacci sequence. And the Fibonacci sequence is kind of interesting. It shows up a lot in nature in maybe kind of unexpected ways. For example, if you look at bees, male and female bees, I'm probably going to get the details wrong, but whether a bee is a male or a female depends on whether the eggs are fertilized or not fertilized that produced the bee, with the result that not every bee has two parents. I mean, if the egg is not fertilized, that bee has one parent. And if you look at a male bee and you trace back the number of bees that it's descended from, you wind up with the Fibonacci sequence. So we're not going to do a lot with it in this class. In fact, I think it's fair to say we're not going to do anything with it, but it's a nice example of a recursive sequence that shows up in sort of natural settings. That isn't just something a mathematician made up to put in a textbook. This example here is significant. We're not going to study it specifically, but the idea behind this is that we're looking for a root. And we start with some value near the root, and then we get closer to the root, and closer to the root, and closer to the root, and closer to the root. But Newton's method will never actually give us the root. It will never get us there perfectly. And this idea that we're getting closer and closer to some value without ever actually reaching it, hopefully sounds familiar. That's a limit. So we can talk about the limit. It only makes sense with sequences to talk about the limit as we go to infinity. The limit as n goes to infinity of x sub n. We say it reaches L, some L for limit, if as n increases, x sub n gets closer and closer to this number L. These are not very fascinating examples. I shouldn't pop them down. But if we look at the sequence 0.9, 0.99, and so on. If we just add a 9 every time. Here's an example of a sequence with a limit. It's going to 1. Every 9 we add brings this closer and closer to 1. 3, 3.1, 3.14, 3.141, there's an example of another converging sequence. I only remember it up to 3 decimals, but we can get a sequence that converges to pi. And all we're doing is we're taking pi and it's this infinite decimal, and every element of the sequence just includes the next entry in that list. And this is going to be relevant, so I'll say it now. A lot of times we think of sequences as basically functions. That was what we were trying to get at, not here. That's what we were trying to get at here. I mean, if you look at, x sub n equals n squared, the sequence, and f of n equals n squared, the function. Well, I guess f of n has a bigger domain. F of n, you can enter decimals, whereas x sub n, you only have 1 and 2 and 3 and so forth. But, otherwise, these are basically the same thing. X sub 1 equals 1 squared. F of 1 equals 1 squared. X sub 2 equals 2 squared. F of 2 equals 2 squared. X sub 3 is 3 squared. And so forth. And I bring this up now because this way of thinking is going to be how we're going to find most of these limits of sequences. Let's say we have a sequence x sub n equals 2n times n over n squared plus 1. And we ask, what's the limit of this thing as n approaches infinity? Well, we don't have any tools for taking limits of sequences. I mean, we haven't learned any special tools. But we can take the limit as n goes to infinity of this expression. In particular, as n goes to infinity, the top is going to infinity, and the bottom is going to infinity. So this is an indefinite form of infinity over infinity type. And we can hit it with L'Hopital's rule. And the only thing is, a lot of times in math and in calculus, we use n as a constant. Here we're using n as our variable, so we need to be a little careful there. The derivative of 2n is 2. The derivative of n squared plus 1 is 2n. And now this is bad notation, but we can live with that. As n goes to infinity, the bottom is going to infinity. And a finite number over infinity is 0. So the reason, or one of the reasons, we learn L'Hopital's rule now, as opposed to back in Calculus 1, when we were doing other limit and derivative stuff, is that for us, this is going to be the main application of L'Hopital's rule. Maybe it goes without saying, but I'll say it. As with every other limit we've looked at, there is no guarantee that a sequence has a limit. And the not terribly exciting sequence of natural numbers, for example, is clearly a sequence without a limit. Or maybe I shouldn't say clearly, but this is not approaching a finite number. It's approaching infinity, if you want to think of it that way. But infinity is not a number, and infinity can't be a limit of a sequence. And this is the same terminology we've used for other limits. If a limit doesn't exist, we say it diverges. And that's sequences. That's section 10.1 it would be. I'm going to, because we have a little time, I'm going to go right into series. Does anybody have any questions for me? So, in English, sequence and series are basically synonyms. I mean, if you talk about a sequence of events or a series of events, you're saying the same thing. In math, they mean very different things. In math, a series is a sum. We're adding stuff together. And so there is a series and we don't need calculus to add 1 plus 2 plus 3. This is a finite series, a finite sum. So since I'm now putting the emphasis on the word finite, you can probably imagine we can also have infinite series. We can add infinite things together and get a finite number. And that's what chapter 10 is really about. And you know, this idea of adding infinite things together and getting a finite result back is one that has troubled people for a long time. I don't know if anyone here is familiar with Zeno's paradoxes. So Zeno was a Greek mathematician, or a Greek philosopher, rather. We only know him through the writings of his enemies, so we might not have a very fair view of what his actual beliefs were. But he's known for arguing, for example, that if you fire an arrow at a wall, it can never hit it. And his argument was this. So here's you, and here's the wall. So let's say you fire this arrow. Well, before it can get to the wall, Zeno says, it has to get halfway to the wall. That goes without saying, and this will take some amount of time. The arrow cannot move instantly. So it can get halfway to the wall maybe, but that takes some amount of time. Well, now the arrow's here, but it can't just teleport to the wall. Before it reaches the wall, it will have to get halfway there. And that will take some amount of time. And you probably see where this is going. The arrow can never reach the wall, because to reach the wall, it always has to do something else first. And that something else always takes some amount of time, ergo the arrow can't reach the wall. And from a modern point of view, we'd say, well, it's true that we have these infinite events, this amount of time and this amount of time and this amount of time, that's all true. And we take these infinite amount of times and we put them together and we get a finite time. And that's how long it takes the arrow to reach the wall. So from a mathematician's point of view, a modern mathematician's point of view at least, the idea that, well, we put these infinite time intervals together, and we get a finite time. I mean, that doesn't bother us, that's calculus. It bothered Zeno, and it bothered his opponents, because, again, the Greeks had no notion of infinity. And we're going to define an infinite series. It's an infinite sum. And our notation is going to be the same summation notation that we used for finite sums, except up here, where for finite sums we'd have a stopping condition. We tell you what the last term is this is an infinite sum. It never stops. We put an infinity symbol up there. And the way we define this, well, everything else in calculus, basically, we've defined in terms of limits. I mean, this is extremely similar to something we've done before. It's extremely similar to improper integrals, where, we want to go from a finite interval to an infinite interval. If you remember how we did that, we defined it as a limit Well, that's just what we're going to do with infinite sums. We're going to define them as a limit of finite sums. Nope, not an n equals under there. So let's see. I'm using n for some. No, but this is fine. A lot of times we use k instead of n. So I want to go from, no, yes. Sorry for that. So n is being used for the upper value, meaning that I can't use n again down here. It would be confusing to use n for more than one thing in the same problem. So the traditional letter is k. We define an infinite sum from 1 to infinity to be the limit of these finite sums. There's a long sort of history behind this definition. For a long time, mathematicians worked with these infinite series without having a very formal definition of what it means for an infinite series to converge or diverge. And most of the time they got away with it, but occasionally they'd run into these series that behaved oddly in ways that they couldn't really understand. And modern mathematicians do not have that problem because modern mathematicians have a universally accepted definition of what this infinite sum is. But as an example of the problem that people like Leibniz were running into, they would look at series like this. So this is an infinite series. It goes on forever. And they'd ask themselves, does this converge? And if it does converge, what does it converge to? And they would try to treat this infinite sum as if it were a finite sum. And they'd say, well, Addition is associative. We can put parentheses in here. So we can just put a bunch of parentheses in here. And now it seems clear that if we have a 0 added to itself a bunch of times, the result ought to be 0. 0 plus anything is 0. But then they'd say, well, we could also rewrite this series as 1 minus 1 minus 1. This is the first 3 terms of the series. 1, this minus sign distributes over this, so this positive 1 corresponds to this negative 1. This minus and this minus cancel, giving you this positive 1 minus 1 minus 1 minus 1 minus 1 minus 1 minus 1. So when we do this, well, subtracting 0 doesn't change a number. So if we subtract 0 from 1 a bunch of times, we ought to wind up with 1. So something is obviously going wrong here. And what's going wrong is that, you know, we're just taking these infinite sums and we're treating them as if they're finite. And we're just assuming that all of the stuff we can do with finite sums works with infinite sums. This series has a name. It's called Grandy's series. A little bit of history, I guess. Grandy was a monk, a Roman Catholic monk. He wrote an entire book on this series. Grandy, as a Roman Catholic monk, imbued this with religious significance because to Grandy, this is an illustration of the idea that you can start with nothing and turn nothing into something. And to Grandy, this was analogous to the idea that God created the earth ex nihilo, that God could create the earth from nothing. It's possible to go from nothing to something. Whether you find that convincing, I will leave to you, but modern mathematicians don't struggle with Grandy's series. The sum from 1 to 1 is 1. The sum from 1 to 2 is 0. The sum from 1 to 3 is 1. The sum from 1 to 4 is 0. So we're taking the limit of this sequence, and this sequence doesn't have a limit. The sequence is not approaching a finite number. It's just oscillating bouncing between two values. Say, well, this has no limit. So Grandy is series, which you'd write as this if you wanted to use this summation notation. Does not converge. Again, as just a historical side note, the before mathematicians settled on this definition, there was kind of a consensus that Grandy's series ought to equal 1/2. That if you add these things together, you should wind up with 1/2. And I mean, you can sort of see the logic. It's oscillating between 1 and 0. So they say, well, if it spends half its time at 1 and half its time at 0, we'll split the difference. But this is not what a modern day mathematician would think. And that brings us to 9:50 and the end of class. I will see you Tuesday. And tests, so either hand back physically or email them back to you, depending.